Hello everybody, my name is Elena Umili from Sapienza University of Rome, and today I'm going to present Injecting Logical Knowledge in Deep Autoregressive Models. So this is a work that was developed within SPOC 5 of the FAIR project. So the main goal of this work is to design a principal approach to integrate domain knowledge expressed in linear temporal logic over finite traces into sequence generation task with neural networks. So sequence generation is generally approached with autoregression. So you can train an autoregressive model, like for example a transformer or a recurrent neural network, in order to predict the future given the history. However, in sequence generation, we may have not only data, but also some domain knowledge expressed in a logic formalism. And it's difficult to use both, exploit both in the training of our system. So an example is the following. So imagine you are an hospital manager who wants to predict future activity of patients to be able to best organize machines and resources of the hospital. You may have data, but you may also have some knowledge of this kind. For example, that treatment A and treatment B cannot be both used within the same course of cure of a patient. That can be translated into this logical formula in LTLf. Or you may know that screening C is a prerequisite to perform surgery D. In order to integrate both knowledge and data, so and train our neural model with both, we estimate the probability that the autoregressive model will satisfy the knowledge given the model parameters, the prefix, and the knowledge, and we encode it in a loss function. So to train the model to both replicate the data in the dataset and be compliant with the logical knowledge at the same time. So the challenges that we faced are mainly two. The first one is that exact estimation of this probability is computationally intractable because the cost of estimating it is exponential in the sequence length. And for this reason, we didn't estimate the exact probability, but we used an approximation made with Monte Carlo. The second challenge is that both the knowledge checking and the categorical sampling are not differentiable, must be done in a differentiable way. So to be able to propagate the loss through the network. And in order to face the challenge, we exploited a probabilistic relaxation of the FA for knowledge checking, and we use Gamble softmax tricks for differentiable categorical sampling. Many results. These results are preliminary ones on achieved on synthetic datasets that were published in this paper. And we have also some new results on real business process management datasets that are not published yet. They're on archive. You can go on this second reference. In both synthetic and real datasets, we found that the knowledge satisfaction of the constraint is highly increased, is close to 100%. And the similarity on test suffixes is similar or higher to the one achieved with the unconstrained model. So we generalize better, and we are also more compliant with the constraint. That was our initial goal. So in conclusion, by exploiting both logical knowledge and data for training the sequence generator makes the model more reliable and also more accurate on test sequences, and also easier to train because we have a number of training epochs that is reduced of more or less 66%.